In the last lesson, the focus was defining acids and bases, looking at their strengths and structures, and as well we looked at how to calculate the pH of solutions that are strong acids or bases. The focus of this lesson is weak acids and bases. The difference comes from the fact that a weak acid or base is a substance that only partially dissociates. Therefore, when we're studying these solutions, we're going to need to set up an equilibrium. First, we'll look at the general reaction for an acid and water. When we're studying a general acid, we use the formula HA. So A is the anion and H is the acidic proton. For the most part, the acids that we will deal with will be monoprotic acids, meaning they will have one proton that dissociates. As you know, the reaction with water involves a proton transfer from the acid to the water to produce H3O plus and A minus. So A minus is that counter ion, so it's the rest of the formula from the acid with a negative charge because it has lost a proton. Now when we're looking at this equilibrium, we can write a Ka expression. So the equilibrium constant, we refer to it as Ka, meaning it's the equilibrium constant for the dissociation of an acid. Like before, it's the concentration of the products over the concentrations of the reactants. And what you'll notice when you look at this Ka is that water has been omitted. Water is a pure liquid. All the other substances are aqueous. And as you know, pure liquids are not included in the equilibrium. Now these constants have been determined, and there is a table of dissociation constants in your textbook, table 15.3 on page 671. We'll look at that in a moment. One other thing to note though is that we can also take the pKa. Before we look at the table, we'll just discuss that briefly. So the P of anything, as you saw from the pH, was the negative log of the concentration of H3O+. The pOH was the negative log of the concentration of OH-. So the pKa, similarly, is just simply putting the values for Ka on a logarithmic scale. So the pKa is the negative log of the Ka value. Inversely, if you want the Ka, you'll take 10 to the negative pKa. We always use a logarithmic scale when we want to be able to manage a really large range of values. So numbers that go from really high to really low. And that's why it makes sense to use a logarithmic scale here. You know, if you look at this table, this is the one that's in your textbook and it's also in your notes. It shows you the formula for some weak acids, right, and their structure, and it gives you the Ka values. Okay. It also gives you the Kb value for the conjugate, which we'll discuss momentarily, but as you know, HF, its conjugate is F minus, so it gives both the Ka value for that and the Kb value for the conjugate. What you'll notice is that they're put in order from largest Ka value to smallest Ka value, and the size of the Ka value really tells you the strength of the acid, or gives you information about the strength of the acid. Because the larger the Ka, the further the reaction has gone to completion, and therefore the stronger the acid. For weak bases, similarly, we need to set up an equilibrium. The general formula for a weak base is simply B. So when B reacts with H2O, it accepts a proton to produce BH plus and OH minus. Just notice a little typo here. This should be Kb. So this is the equilibrium constant for the dissociation of this base, and the concentration of BH plus times the concentration of OH minus divided by the concentration of B will give you the value for the Kb. Again, there's a table that summarizes some of the most common weak bases. And with this scale, we can produce a pKb by taking the negative log of Kb. So these new relationships between pKb and Kb and between Ka and pKb can be added to your toolbox for acid-base chemistry. Here's the list of common weak bases, and again, the higher the value for the Kb, the stronger the base is. And what you'll notice is that the bases are all nitrogen bases, so they've all got the nitrogen, and it's actually highlighting in the structure by showing the lone pair on the nitrogen where those hydrogens will actually attach. Okay, now let's look at a few examples here. So we need to be comfortable writing the reactions, and we also need to be comfortable with writing the Kb and Ka expressions. So with hydrazine, it's a weak base. So if we want to write the equation for the base, we need to add it to water. So we've got N2H4 plus H2O. It's a weak solution, so it's going to be in equilibrium. The proton is going to be transferred from the water, so we are left with N2H5 plus and OH minus. And the corresponding Kb is the concentration of N2H5 times the concentration of OH minus over the concentration of N2H4. We can also identify the conjugate acid-base pairs if we wanted to. This is the base, and the conjugate acid is the N2H5 plus. Water is acting as an acid here, and the hydroxide is its conjugate base. So what you should do at this point is pause the video and complete number 2, and we'll take those up in class. So you need to write the equation, identify the conjugate acid-base pairs, and write the Ka or Kb expression. At this stage, I'm identifying whether we've got a weak base or a weak acid, but I would like you to start to recognize or look at the formula and understand why we could tell that it's a base or an acid. So with the bases, we're looking for the nitrogen, okay? And with the acids, we're looking for that COOH group. So in this case, okay, it's a little bit hidden. This is the acidic proton here, but if you draw the structure of the formula that you're given, you'll see that it's an acid. In question number 3, it compares methylamine and pyridine, and it gives the Kb values of 4.4 times 10 to the negative 4 and 1.7 times 10 to the negative 9, respectively. And it's asking which is the stronger base. So as you know, the strength is related to the extent of the reaction. So when we're looking at the K value, the larger K results from a stronger acid or base. So in this case, the stronger base is therefore methylamine, or CH3 NH2. So in the last lesson, we looked at how you could compare two acids or bases just based on their structure. This time, you've got a value to support your argument. Now in the next one here, we've got two acids, HF and HN3, that have pKa's of 3.17 and 4.74 respectively, which is the stronger acid. Now first let's just address this one here. This is an unusual looking acid. This is one where I would definitely tell you that it's an acid because it would be hard for you to make a decision. And the HF you should recognize as an acid. Now I'm giving you the pKa this time of 3.7 and 4.74. And as you know from studying the pH scale, the lower the pH, the higher the concentration of the H3O plus ions in solution. So the higher the pKa, okay, will be the smaller the Ka value. So if we want the stronger acid, we need the pKa that is lower here, because this will result in a larger value of the Ka. If at any point you're unsure and you can't remember the rule or you're forgetting for some reason, you could just simply convert both of these to their Ka values by taking 10 to the minus 3.17 and 10 to the minus 4.74. And you'll see that HF is the stronger acid. Okay, and the argument for that, the explain, okay, is because it has a larger Ka value. And the reaction proceeds farther to completion. The next thing that we're going to look at is the relationship between Ka and Kb. And the relationship that we're looking for is when we are dealing with an acid-base pair. So a conjugate acid-base pair, we want to know what the relationship is between their respective Kas and Kbs. So if I go back, if we're looking here, we've got ethylamine and it's got the Kb. And then it gives us the conjugate and it gives us the Ka for that. And there's a relationship between the Ka and the Kb for a conjugate acid-base pair, and that's what we want to determine. The way that we're going to determine that is by using some skills that we learned in the last unit, where we add equations. So what I've done here is I've written the reaction of a base, NH3, and its conjugate acid, NH4 plus, in water. So NH3 plus H2O, this is my base, so it accepts a proton to become NH4 plus, and we've got hydroxide. This conjugate acid in water donates a proton to produce H3O plus and NH3. When we look at their expressions, we've got Ka and Kb, which are simply the equilibrium laws for these reactions. Now, when we add these two reactions, what we can see is that the NH4 and the NH3 are on both sides of the equation, so they can be deleted as we add these reactions. And what we're left with when we've got these two water molecules is 2H2O in equilibrium with H3O plus and OH minus. So this equilibrium, it has its own equilibrium law, which is H3O plus times OH minus. And hopefully you recognize that as Kw. So this reaction is the reaction of the dissociation of water. And we learned in the last lesson that the equilibrium law for this is a special one called Kw. So when we add these two reactions, and with any conjugate acid-base pair, if you add the acid reaction to the base reaction, you're always going to get this particular reaction. And as you know from the last unit, when you add two reactions, the equilibrium constants multiply. So what we see developing here is a relationship that Ka times Kb is equal to Kw. So Ka times Kb is equal to Kw, or 1 times 10 to the negative 14. Which also leads to the pKa plus the pKb equaling 14. If you take the negative log of both sides of this equation and apply your logarithm rules, you will get this relationship of pKa plus pKb is equal to 14. Or you can also recognize the connection between the two reactions, this one and the reaction up here. Okay. If we take the negative log of both sides of this equation, we get POH plus pH is equal to 14. Okay, so it's the same thing. Now in your notes, there's space for you to do a second proof if you would like to do that. Okay, it will help you to practice writing reactions in water. Okay, and it will help to affirm the fact that whenever you add reactions that are from a conjugate acid-base pair, you always get this reaction here. Okay, now when we look at this equation here, we want to look at the conjugate bases of these, and we want to compare and determine which conjugate base is stronger. Okay, because they are very different, okay, we don't really need to do too much of a calculation here. But first, let's look at what the formulas are for the conjugate bases. Okay, so the conjugate base of the first one is going to be COOH negative. Okay, because remember, an acid is losing a proton, so we take that away. For the second one, it is Cn minus. This is the Ka value for the reaction. So we know that Ka times Kb is going to be equal to 1 times 10 to the negative 14. Okay? So what that means is that the order of the Kb, okay, is going to be 10 to the minus 10, okay, because this one here is 10 to the minus 14. Okay? If you multiply two things, okay, so if I multiply 10 to the negative 4 by 10 to the negative 10, I add the exponents, and I'm left with 10 to the negative 14. This one here, Kb is going to be approximately 10 to the minus 4. Okay, because they're so far away from each other, I don't need to worry about being off because I'm really just estimating here. But this is a good example of a time when you can estimate to answer the question. So when we look at this, it's asking for which of these two is stronger. Okay, and this one has a larger Kb. Okay, so this one is stronger. This also gives you an important relationship. The stronger an acid is, the weaker its conjugate base is going to be. Okay, because of this relationship, as Ka increases, the Kb must decrease in order for this to be true. So if we apply that to something like HCl, okay, HCl is a very, very strong acid, so it's going to have a very large Ka value. And what that means is that its conjugate is going to be very weak and virtually not really that basic. Now, the meaty part of this lesson is about to begin, and the focus here is to look at how we can perform equilibrium calculations, much like we did in the last unit. So the goal from the last unit, when we set up ice charts and did equilibrium calculations, was to find equilibrium constants or find equilibrium concentrations. And in this case, when we're finding equilibrium concentrations, it's going to help us to find the pH of solutions. So the setup is going to be very similar. There's a few main differences. So first, let's look at an example where we're going to find the Ka of a solution. Okay, so in this example here, we've got acetyl salicylic acid, which is aspirin, and it tells us that it's a weak monoprotic acid. It says in a 0.1 molar solution of this acid, it is found that the pH is 2.24. What is the Ka value for this acid? Now we've come across one of the main differences between the problems in this unit and the problems in that unit, the last unit. And this is that we're not given an equation to deal with. We need to make our own equation. So when you're dealing with acids, there's not a reaction with anything here except for water. And in this case, I haven't been given a formula, but I've been told that it's a weak monoprotic acid, so I can use the general formula for the acid, which is HA. Okay. Now, as in the last unit, we're going to set up an ice chart. And in this case, if it gives us the concentration of a solution, that is the initial concentration of the solution. So we prepare the solution by dissolving some kind of solid in water, and this is basically like the intended concentration of the solution. So I prepared a solution, okay, of 0.1 molar HA. Now water, we don't need anything about it in the equilibrium because it's not included in the equilibrium law. When I first prepared the acid, initially there's no H3O plus or A minus. Okay, from this we can record our changes. Okay. Now, the other really main fact that you need to know when you're dealing with acid-base equilibria is that the pH or the pOH is related to equilibrium concentrations. So that toolkit of pH formulas is going to be very important. Okay? And we need to recognize what to do with the pH that's being given. Okay, so the pH of this solution that we've made is 2.24. From that information, we can find the concentration of the H3O plus. So the concentration of the H3O plus is 10 to the minus pH, or 10 to the minus 2.24, okay, which is equal to 0.00575. Now, because the concentration of the H3O plus is the concentration at equilibrium, what that means is that I, by knowing the pH, actually know the value of X in this scenario. So I know the value of X, so I can solve for the concentration of the HA at equilibrium by taking 0.1 and subtracting 0.00575, and I get 0.0942. Okay, the X value I know, so now I can solve for the Ka. Okay, the Ka is 0.00575 squared, okay, because it's X squared, divided by 0.0942. So the Ka for this reaction is, for this acid, sorry, is 3.51 times 10 to the negative 4. Okay, so to review the main differences, one, you'll not be given an equation. You'll need to write it yourself, and it will always be the equation of the substance in water. And number two, the pH gives you information about the equilibrium. The strategies beyond that are the same. Now this is the opposite type of problem. So in this case, we are looking for the pH of the solution. So we've got vinegar and it's got a concentration. So in this case, if it was analyzed, that means that we did a titration. So much like you did the titration last year with vinegar. And you determine its concentration by the titration. Okay, that is the initial concentration of the acid. Okay, water is not included. Okay, so I can pretty quickly set up my ice chart for this. Okay. Now in this case, I want to know the pH. So I want to be able to find the X value. If I can find the X value, then I can find the pH and the H3O plus in solution. Now, the other difference with these problems is that a lot of the times you're not actually given the Ka value or the Kb value in the question, and you need to use table values to determine it. Okay, so don't be thrown off by that. Sometimes people think they don't have enough information to solve the question because they haven't been given a particular K value. Okay, if we look this up for vinegar, it's 1.8 times 10 to the negative 5. Now, the other really nice thing about solving acid-base equilibrium problems is that the Ka values are often quite small. Okay, so it's very, very rare that you would need to do much math in order to solve them. We're going to be able to make the assumption. So in this case, because it's small, I can assume that this is approximately equal to 0.75. So I've got x squared over 0.75 is equal to 1.8 times 10 to the negative 5. Okay, so when I solve, I've got 0.00367. So I know the x value, okay, which is the concentration of the H3O+, so I can report that because I was asked for it. Okay, and I should have rounded this. So I'm just going to get my eraser here. Okay, I should have rounded this to 0.37. Okay, the pH is going to be the negative log of that. And when you find the pH, it's 2.43. Now, in terms of significant digits, we need to really make sure that we don't round too early, especially when we're finding the pH. So here I've got 2 significant digits. So when I'm finding my x value, I'm keeping a minimum of 3. Okay, if you want to use your calculator and keep all of them, that's fine too. But if you keep a minimum of 3, you should be fine. Okay. Finding the pH, I report it with 2 decimal places to reflect the 2 significant digits. The next problem here is to find the percent ionization of HCN. Okay, so if we look at HCN, okay, I'm running the reaction in water. Okay, this has nitrogen in it, so it's not that obvious that it's an acid, okay, but it is an acid. Okay, and it has a Ka value of 4.9 times 10 to the negative 10. Okay, if I set up my ice chart here, I'm obviously writing too close to the edge there. Okay, and the HCN is 0.1. My H2O I don't worry about. Okay, these increase by X. Okay, and because it's so small, I'm going to be able to make the assumption. So I've got X squared over 0.1 is equal to 4.9 times 10 to the negative 10. And when you solve for X, you find that you get 7 times 10 to the negative 6. Now in this case, it's not asking for the pH. I could find the pH. It's asking for the percent ionization. So what it's asking for is the percent of this 0.1 molar HCN that has been ionized. So the amount that's been ionized is X, or this value. So if we report that as a percent, it's going to be 0.1. Whoops, sorry. It's going to be the change or the X value divided by the initial concentration. This formula is written above in the notes if you want it for reference. Okay, and what we find is that this percent ionization is 0.007%. Percent ionization, in the last unit, you were actually doing percent ionization when you were checking to see if making the assumption was valid. So it's the same calculation, but we use the terminology percent ionization. Now what I'd like you to do at this stage is to finish the note by answering questions 4 and 5, okay, and we'll take those up next class.